I've started recording it anyway. So yeah, fine. People will join us to continue. Yeah. So yeah, we were talking about this thing of modulo and what that means exactly. And I'm actually, again, the way I normally usually teach at times, I may be a little bit chaotic. They're not organized, but at least you get the concepts right. So one thing I've thought about that actually I can shed light on, especially now with this thing of the remainder, which we normally call the the remainder. When we divide A by D, we get R as a remainder. We can call this mod. And now I was just describing to you, like when you talk about mod 11, whatever integer you take, you divide by 11. You remember one thing we talked about last week anyway. We talk about mod 11. It means that, when you divide the set of integers by 11, the possible remainders you can get are either the number is divisible by 11, in which case the remainder is 0, like 110. So we say 110 mod 11 is anyway, that's mod 11, this is 0, right? Why? Because the remainder is 0. So when you take any other number, like what, a number that is divisible by this, you just add 11 to this, you get 121. 121 mod 11. Again, this is 0. Mod 11. This is 0, and those numbers that are divisible by 11, the remainder will always be 0. The numbers that are divisible, we divide by 11, the remainder is 1. Those numbers will be 1. Mod 11, the 1. So something like 111, 122, and so on like that. So the possibilities of those numbers will be 0 to 10. So if we are looking at the integers, we were talking about partitioning last time. You can partition them into 11 compartments, 0 up to 10, and so on like that, okay? Now, this can also come in another aspect, which I thought of talking about. Again, you forgive me for jumping the notes and something going here. Let me go where? Here. Don't worry, all this will be covered eventually. Probably I can come here or no. Yeah, okay, here. These are concrete examples you can solve, basically saying, determine the value of 19 cubed mod 31 power 4 mod 23. So what does that mean? Now here I ask you to whip out your calculator or whatever it is you're using to compute. You compute 19 cubed mod 31. What does this mean? From the context of what we were just talking about, this is just saying you take 19 cubed, you get 6,859. So mod 31, this means when you divide 6859 by 31, you see what happens. You will get 221. This is a quotient they have divided for you. You get 221, and the remainder will be 8. 221 times 220, 31 times 221 plus 8 gives you this number, which is 19 cubed. So that means 19 cubed mod 31. This number here is 8. So now the next one is power 4. So you just have 8 power 4 mod 23. So 8 power 4 is 4096. So 4096 or 4096 mod 23, this just means if you divide this number by 23, what will be the remainder? And so it turns out that when you divide 4096 by 23, the quotient will be 178 and the remainder will be 2. So that means now we go back. So the whole original question was asking, the value of that whole thing is 2. And you can see this is interesting because sort of you reduce the numbers that you have there, look very complicated to very simple numbers, all right? So there you have one nice example. Number 2 is here. Now allow me to wrap this one. I hope everyone has managed to come back. I'm only seeing 5 people. Some people have gone for lunch or whatever it is, but no worries anyway. Hopefully they'll manage to get in. In this case, now you have 89. Determine the value of 89 cubed mod 79 power 4 mod 26. So again, what are you asking to do? Well, you are supposed to take 89 raised to power 3. You get this number here, 700,000, 704,969. Then mod 79. No, wait, what are we saying? Yeah, so this number is this mod 79 power 4. So mod 79, this part, allow me to get my arrow here for pointing. So that means is when you divide this number by 79, what will be the remainder? So you can compute that. Okay, I mean, if you want, you can compute, but it turns out well, it is here actually, I did the computation for you, that 704,969 divided by 79, the quotient is 8923, and the remainder is 52. So here, this number here is 52. Then power 4. Actually, here I can tell you something else that I would want you to be noticing, to make your life easier. And what is that? That now if you take, you see, now we've computed this number, it turns out to be 52. So this now here translates to, this equals 52. Well, it's already written here, but anyway, maybe I get excited when I write like this. 52 power 4 mod 26, okay? Now I want you to see something which is more like a shortcut thing. What do I want you to notice? That 26 is the same as, 52 is 26 times 2. So already this means 52 is a number that is divisible by 26, right? So you don't need to do all those. Of course, you can punch in to get what 52 power 4 is. But in this case, I can tell you, you don't need to do that, because you can see 52 is 26 times 2. So that means whatever, this number raised to power 4 is still divisible by 26. So the remainder is 0. So it turns out that this number is simply 0. And that's beautiful, isn't it? Yes, it is. Okay, so that's that. Now let me see what else we can say about this. Now here, okay, so with those remarks, allow me to go back to the, so far so good, I hope. And everyone else has come back. So now let's go back to where we were so we can continue. To allow me to remove this. So these results, I've said that we will see it later on, this particular result number 3, theorem 3. So now we go to the next thing, which is, this we've looked at, this we've looked at. Yeah, so this is what we were talking about. So let's look at this. With what we have talked about now, I think you have a bit more understanding. So let m be a positive integer, a and b be in any integers. Then we have two results. One is a plus b mod m, basically the remainder on division of a plus b by m equals the sum of the remainder on division of m by, a by m and the division of b by m. When you add the remainders, the remainder of that on division by m equals that, okay? So proof of this is actually not very complicated. So there's some shaking here. I don't know whether it's a tremor or whatever it is, but anyway, if it is, well, fine. We thank God we are safe. So far, so good. Right. So first we change the notation. So the notation is to say RA, let RA, this be the remainder on division of A by M. Remember, that's the definition. M mod M means that the remainder of division of A by M, and then the remainder of division of B by M, we call it RB. So that means we talk about remainder on division, it means that A divided by M, you get some quotient plus remainder. And B, you divide by M, you get some quotient and the remainder. So if you add these two, you get A plus B is the same as, the left-hand side, which is A plus B, equals the right-hand side, which is this whole expression plus this whole expression, which will be M. You pull out the brackets, you have the quotient, sum of the quotients, plus the sum of the remainders. And so what does this tell you? This tells you if you divide A plus B by M, you get this quotient, and this will be the remainder. In other words, the remainder on division of A plus B by M is RA plus RB. Now, these ones, you can also interpret them as saying that this is just the remainder on division of A plus B by M is this, the sum of these two guys. And this we already have the notation that A mod M plus B mod M. All right. So the remainder on division of this number by M is this. So we can translate and say this is it. This is saying that. I hope it makes sense. So otherwise, that's it. So a test of whether this makes sense is to try and do part two, which I don't want to, I will say you think about it. If you get stuck, you can always call me anytime around. Otherwise, I would like to proceed. Now that has covered my 10 minutes, okay, around. Next is this we've looked at, this we've looked at. Now this one, is more or less pretty straightforward. I can actually tell you again. When I say pretty straightforward, I don't mean the usual English. I mean the English for mathematics. But let's just look at it briefly and quickly. So prove that if a, an integer a that is not divisible by 3, then there are two possibilities. A plus 1, I mean, then a plus 1 times a plus 2 is divisible by 3. Now here, I don't want to be, I mean, I will say you go through the proof. I will just tell you this again. I'm giving you shortcuts of way to think very fast. When you talk about any integer, we are dividing by 3. When you pick any integer, you divide by 3. What are the possibilities? That the remainder is 0? Remember, I was using this notation to mean all those numbers. When you divide by 3, the remainder is 0. Or the remainder is 1. So, for example, 3, 6, 9, all those numbers will be here because when you divide 3 or minus 3, 6, minus 6, 9, minus 6 by 3, you get no quotient, I mean remainder. So the remainder is 0. If you pick something like 4, you divide by 3, you get 1 remainder, 1. You get something like 7, divide by 3, you get 2 remainder, 1, and so on like that. Or the last one you get is when you divide by 3, the remainder can be 2. So on division of any integer by 3, there are only 3 possibilities. Either the remainder is 0, 1, or 2. So now this statement is telling you to prove that if the division by 3, well, rather, if you pick an integer that is not divisible by 3, then the sum of the product of a plus 1 and a plus 2 is divisible by 3. Well, you can see that it is true. You know why? Okay, the proof is that one. I don't think is very complicated. But basically, when you say it is not divisible by 3, you know what you do? You have ruled out this case. So you're only either dealing with this or this. This statement is just saying that if a number is not divisible by 3, an integer, then either it's here, the remainder is 1, or it's 2. So if the remainder is 1, for instance, something like 4, all right? So my A is 4. That means if I take 4 plus 1, I get 5, right? Times 4 plus 2. So this is saying that this number is divisible by 3. And of course, it has to be because, you see, if it's either this one or here, it means that when you add 1 or 2, 1 for one case and 2 for the other one, then one of them becomes divisible by 3. You can see this is 6 times whatever it is. So this is what the theorem more or less says. And I leave it at that. I mean, if you were dealing with division by 4, the same thing would happen. By 4, you'll have 0, 1, 2, and 3, and so on like that. Again, ladies and gentlemen, I'm just giving you sketches. I hope they make sense. If they don't, you can always stop me now or later. So far, so good. I hope so. Can I proceed? I hope so. Let me see who is around. Everyone is around. Life is good. I hope. So here we are again, ladies and gentlemen. Doing what? Doing something that looks very similar to what you've just seen. This is nice, actually. So let's go through it very quickly, or whatever speed we shall use, I don't know. Now, here you are given an example. What are you supposed to do? Suppose A is congruent to 4 mod 13, and B is congruent to 9 mod 13. So find C such that, C lies between 0 and 12. Now this, ladies and gentlemen, I don't know why this is the same thing of modulo 13. Remember when you said when you had modulo 11, it was 0 to 11. So you talk about modulo 13, this is what you have. It means that this modulo 13 is just 0 to 12. So now let's look at this. And now you already know something about congruence modulo. So let's look at this. So find C such that, A, B, C. First case is C is congruent to 9A mod 13. The second one is C is congruent to A plus B mod 13. And last one is C is congruent to A cubed minus B cubed mod 13. All right. So here I just look at 1, or maybe B and C, or whichever it is, very quickly. Okay. Sorry. Yeah. So Now, let's look at this. So here you're looking for C that is going to 9A mod 13. So what is it? I don't want you to look at the solution. The solution you've had the notes anyway. So how you tackle this is to try to bring in, you see, use what you already have to make this that you are working out look like what you have. What do you have? You have A is congruent to 4 mod 13. So the first thing is this one, I can say this one, you can change it and say this. Now, I want to say A is congruent to 4 mod 13. I can also say 4 is congruent to A mod 13. Do you agree with me? Of course, I've already said it, and it is true. It's based on what I told you last time, and I based on what I've told you today. What? I mean, if A, this is just saying 13 divides A minus 4. So, of course, 13, if 13 divides A minus 4, 13 also divides 4 minus A. So, if you change the order, it's still okay. So, A congruent to 4 mod 13 also carries with it 4 is congruent to A mod 13. And now, this is looking like where you want to go. Now, I hear some noise. I don't know, is someone coming or whatever it is. Yeah, anyway. So, already now we are getting somewhere. So the next thing is just to say now we need to make this A into 9. So if you multiply this by 9, now there's something else which I don't know whether you remember, but if you don't, I can remind you. It's not very complicated. The good thing is the notes are here, so here it is. You see this? These two we have proved last time, and today I can claim. I mean that you can actually add congruent modulo. So A, as long as A is congruent to B mod M and C is congruent to D mod M. So if I add, I can say A plus C will be congruent to B plus D mod N. And likewise, if I multiply, if I multiply both sides, like in this case, I'm multiplying by, C, and these are multiplying by D. So A times C, then I have B times D. So I can bring in multiplication and it still remains valid. So in this case, what you have, if you see, is that I want to make this 4A, this A into 9. So all I do is just multiply. So if multiply by 9, this side I'll have 9A mod 13, right? I hope I'm recording this. Am I? Is it recording? Yes, it is recording. Okay, fine. Mod 13. And so on this side, what I've done is I multiplied by 9. So this also is multiplied by 9. It becomes 36. So 36 is congruent to 9A mod 13. So that means our C is 36, but then C must be mod 13. So 36 now has to be converted to mod 13. And now that's what we were doing not too long ago. And why are we doing that? Because it told you to find C such that C lies between 0 and 12. Now this C of ours is 36. So for it to lie between 0 and 12, you have to divide by 13 because of mod 13. So when you divide 36 by 13, what is the remainder? You will get 26, if I'm not wrong, right? And then the remaining is 10. So our C is 10. So that's how you deal with it. I hope it makes sense. Clear? Can I claim that the other two will not be very complicated? Okay, let's look at B, maybe or C. I don't know which one you would want. For addition, I will say that's not too complicated. Let's look at part C. Part C is look for C such that A cubed minus B cubed mod 13 is our C. So you use what we have. What do we have? We need to bring in A cubed. So here we can bring in A cubed here. So that means we cube this guy and this guy. So we'll be talking about A cubed. When you cube 4, so I'll have A is congruent to 4 mod 13, right? So what do I do? Well, I cube A, so I cube 4. So I'll get A cubed, and then I cube 4. 4 times 4 times 4 is 64. So I'll have A cubed is congruent to 64 mod 13. Then for B, I do the same thing because I need to bring in cubed. So if I cube B, I'll be talking about B cubed is congruent to 9 cubed mod 13. 9 cubed is 729. So I have these two. And then now, since we are subtracting, we can just subtract these two. We'll be talking about A cubed minus B cubed. minus b cubed. Whoopee. Now my handwriting is bad, but you can read. So if we subtract a cubed minus b cubed, this should be congruent to what? Should be congruent to, yeah, what did I do? Well, the difference, which is 64. No, actually what I did is to convert this to mod 13 and deal with it. So here, what I did, okay, you can do two things. One, you can just say 64, you subtract 729. So that's the number you write here, mod 13. Of course, you'll have something negative, which is fine, no problem. Or you can do what we did before. You can reduce this number to modulo 13. That means if you take the remainder on division of 64 by 13, it turns out to be 12, by the way. And the remainder of 729 on division by 13, it is 1. So then I will be talking about a cubed is congruent to, instead of 64 minus 729, it will be 12 minus 1, which is 11. And so our C is 11. Ladies and gentlemen, I hope that makes sense. That's about it. Now let me just, one moment here. I'm going to mute myself for 1 second. Hi, okay, I continue. So that's the end of that one. If there are any questions, I will answer them. But for now, I want to go to the other agenda I had for the day for you. Now, some people here will want to eat lunch because I'm sitting where they should be sitting to eat their lunch. But anyway, no worries. We'll continue. Right. Next is, let me see where we are at. Okay, so this one for congruence modulo. Let's go through this proof. Let me see whether I will be compromising noise-wise. If there's noise, too much noise, you just let me know. I adjust. Either way, we don't have too much time. I'm assuming maybe 10 minutes again coming up. So now this is a theorem which I said we will see previously. So let's look at it now. So it says let a and b be integers and m be a positive integer. Then a is congruent to b modulo m if and only if, this is the same as in abbreviation, you can just write if and only if, just two arrows like this. If and only if the remainder on division of a by m is the same as the remainder on division of b by m. So the proof of this is not very complicated actually. So the first thing is you set those things. So suppose a is congruent to b. Since we are talking about if and only if, it means we assume this and show this. So suppose or assume or let a be congruent to b modulo m. And something else you can suppose also is that you do have this. You see, since we're talking about a being congruent to b mod m, you can talk about divisibility by m. So you can divide a by m, you get a quotient a with a remainder a. So this is what we're calling the remainder on division of a by m. And then you have b, you divide by m also, you get a quotient b. And then the remainder is rb. So suppose you have that. So what does this imply? That m divides a minus b, right? Which just implies that there exists some integer r such that a minus b equals m times r, all right? And now you write a and b in terms of these two expressions. So you'll have a, which is mq plus ra, minus b is mqb plus rb. And this equals mr. So from this, you factorize the m, you end up with m times qa minus qb, this should not be there, plus you pull out the m, so it's ra minus rb. And now you have these two equations. M times this guy plus something equals m times r. So you know what that means? On this side, you have no constant. I mean, I can just say a constant c, which is not there. I mean, it's 0, I mean, here you have m times some integer plus an integer. Here you have mr plus 0. So that means, what does this translate to? It translates that this part is equated to 0. Ra equal minus Rb equals 0. And what is Ra? Ra is the remainder on division of A by M, which we are calling M mod M. And B is the remainder on division by B by M. So they are equal. And this is what we were proving. And then conversely, these two arrows are, now we are assuming this, we go backwards. So suppose the remainder on division of A by M equals the remainder on division of B by M. What does that mean? RA equals RB. What does that mean? Now you translate, you go back to the beginning. And so that's the end of the proof, ladies and gentlemen. I claim that that is done. This you need to practice again in case it doesn't make sense. Most probably may not. But again, you're supposed to do your 10, 15 minutes. So I hope you are doing that. Now let me see how much time I have based on my location. All right. Oh, I want to erase, but now I'm getting some other things here. All right. Now, the other thing that I had hoped that you will look at, this is now the representation of binary integer representation. So this, I will ask you to look at them because now the last thing I want to look at today, because I didn't want to make these videos too long either way, is the issue of the division algorithm. So this part, let me just remove this. This part I would want you to look at it. Base 10, binary, octal, hexadecimal is not very complicated. The only aspect of this I want you to capture, or I want you to notice, is the representation of these numbers in different bases. It depends on this divisibility. Depends on this. On what? On this. It depends on, where is it? Depends on this. You are dividing, what we are calling the division algorithm, okay? So let me go. So this, please read this and look at the exercises. They are not very complicated. Let me see how much this thing I wish it could warn me, but I think I have 10 minutes. So in 10 minutes, let me see what I can look at. GCD. Can we look at GCD? Yes, 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 yes. Actually, we are doing very well, ladies and gentlemen. I will ask, no, I will not ask. Let's just continue. Okay, so for this one, we have agreed that you will look at it. If you get any problems, you can let me know. Now, I will ask you to one moment. Let me just pause so I move locations. Okay, guys, I'm back. Now here I have doing these things at home on a holiday. These things happen. Anyway, fine. I've changed location now. So we have agreed that you will look into this binary or whatever it is, integer representation of bases, binary expansion, base 8, octal expansion, base 16, and then look at those examples. I believe you will be okay. Now, allow me to go here now. Primes, GCDs, and greatest common divisors. This is now this was my agenda for the day. So, an integer, P, well, we know what a prime number is. What's a prime number? A number that, if you go to integers, we're thinking of positive ones. The number is divisible by itself, only itself, and 1. Then those numbers are called integers. So, they're called primes, okay, prime number. And if the number is divisible more than itself, other numbers, then it's called a composite, okay? So the integers we think of is 2, 5, 3, 5, 7, 11, 13, 17, 19, and so on like that, okay? Those are the numbers that are only divisible by 1 and by themselves. Perfect. We have 10 minutes, so this I can make use of them. All right? And so now all the numbers can be factorized, what we call prime factorization. An integer greater than 1 can be written uniquely as a prime or as a product of 2 or more primes, where the prime factors are written in order of non-decreasing size. In other words, 2s and so on like that, okay? So let me give examples. The prime factorizations of 100, 641, 999, 1024 are 100 is 2 times 2, which is 4. 5 times 5, which is 25, and that's 100. So this is just 2 squared, 5 squared. These are powers of primes. We are done. 641 is a prime number, so it's just 641 times 1. We are done. 999 is 3 times 3 times 3 times 37. Is that right? Yes. 3 times 3 times, well, this is 99. Yeah. So 3 cubed times 37. So that now those are the primes, and that's that, okay? Next, Now there's a theorem here, which I don't know whether it will make sense for you, but let's just do it very briefly. So if n is a composite integer, then n has a divisor less than or equal to the square root of n. It's a way of finding integers, actually. I mean, where they are primes, okay? So here, I don't know if you remember, when you say a composite, it's numbers that are something like 4, 6, 12, and so on like that. Okay, 100 is not prime, you can see, whereas 641 is prime. 999 is not prime, it is composite. So what we're saying is that when number is a composite, if n is a composite integer, then n has a prime factor less than or equal to the square root of n. So the proof of this is by contradiction. What does it say? So contradiction means we assume the opposite of what we have. We suppose n is, so n is a composite integer, right? So if n is composite, then there exist a and b such that n equals a times b. So now what I'm not telling you here, let me just write here so that I make your life easy. Now, the idea of contradiction, here I want you to get this. This is if, then. So basically I can call it P, if P, then Q. So I just want to sketch for you the proof of this in a understandable way. So if P is basically n is a composite integer, then n has a prime factor less than or equal to the square root of n. So now, the proof by contradiction, in this case, we need to assume it's a contradiction for this case. Now, I don't know whether you remember when you're dealing with implication, when you're doing logic, the only time this thing doesn't make sense is when this is false and this is true. Because true implies false would be false. Otherwise, it is true. So this is the only case we assume. We suppose that P is true and Q is false and see what that makes sense. That's what I mean by contradiction here. So I hope that makes sense. So suppose n is a composite integer, and then we suppose that n, in this case, we're talking about n has a prime divisor less than or equal to the square root of n. So in this case, we're assuming to the contrary. So assume to the contrary that n equals ab is true. What this means is n is composite, means that you can find two integers, a and b, a times b, n equals that. That's the idea of composite. And then you assume that this part is false. Now, this part false means what? That it does not have prime less than or equal to this. That means a is less or equal to the square root of n, or b is less or equal to the square root of n is not true, it's false. You see what I'm talking about? True, false, the first part. So, this is false. Now, the idea of this being false means that, now, again, something else. Now, please go away and finish my class. So, and close the door. Close this door. Close this door. Close the door and don't ask me questions. Close. I have a few minutes. So, what this means. Now, the fact that this part being false means what? This being false means that both of them must be false. That means a is less or equal to the square root of n is false, and b is less or equal to the square root of n is false. Remember, this is this part or this part false means both of them must be false. So the conclusion, this says that this part must be true. That means, this false means a is not less than the square root of n. So that's the same as saying a is greater than the square root of n. And b is not less than the square root of n, means that b must be greater than the square root of n. These are true. So that means if you take the product of these two guys, you're talking about a times b is greater than n. And this contradicts a equals b. So that means what we claimed before should be true. So the only time this will not make sense if we assume this part to be false and this part to be true. Otherwise, it's true all the case. So this is saying that, so if n is a composite integer, it's not a prime, then n has prime factors less than or equal to the square root of n. That's how you find in prime numbers, okay? Now, here I had an example for you. I don't know whether this makes sense. I'm sorry, I'm running. I shouldn't. But now a quick example here was saying how you find the primes. I will just go very quickly. I think we have 4 minutes. I've even just jumped all through. So show that 101 is prime. How you check that is now you look at in terms of square root. So the square root of 101, what are the square root of numbers that are less than the square root of 101? 101 is very close to 100. So 100 would be 10. So the primes that are less than 10 would be 2, 3, 5, and 7. So now you check. Because 101 is not divisible by 2, by 3, by 5, and 7, then it follows that 101 is a prime number. That's basically it. Then you can also find the prime factorization of a number. So in this case, you are talking about 7,007. So you will be talking about primes. Now, if you find the nearest, so divide 7,000 by 7 by successive primes, starting with the smallest as you go up. So you divide by 2 is not possible. All right. So starting with 2, 3, and 5. So 2 does not divide 707. 3 does not divide 7007. 5 does not divide 7007. So the next prime, well, actually would be 7. So 7007 divided by 7 gives you 7 times 1001. Then now this you divide by the next primes. In this case, you divide by 7 again, you get this. Next, you divide by 7 if it is possible, and it actually possible. So 7 does not divide 143, but 143 is 11 times 13 if you divide by the next prime. So it turns out that you actually factorize this number into, well, that's one way of something I've not told you here, that here when you're looking at these numbers, you're actually factorizing these numbers into prime powers. So that's that. Let me see. I have my last 2 minutes, which now the last 2 minutes was this issue of GCD. So allow me to define GCD and then I end the lecture. Okay, so greatest common divisor, we'll call it GCD. Let A and B be integers, both, both not zero, yes, they're non-zero integers. So the largest integer, D, that divides both A and B is called the greatest common divisor of A and B. And we denote it by GCD of A and B. So there are those numbers. So example, I have 24 and 36. These are two numbers. Now this, let's just erase this so we can have a clear board in as much as we are running. Hopefully we are good. So what is the greatest common divisor between 24 and 36? So what numbers divide 24 and what numbers divide 36? In this case, it turns out that, I mean, you can see the positive common divisors of 24 and 36 are 1 divides 24, obviously. 2 divides both. 3, they divide both. 4 divides both. 6 divides both. 12 divides both. So of those numbers, the biggest is 12. So the GCD of 24 and 36 is 12. Then the LCM, I can tell you, you look into that, okay? Now I have less than a minute, so the lecture is almost ending. Do you have any question or comment? So the next lecture will be now how we use, let me just rush here. The next lecture will be about Euclidean algorithm. In other words, how to find GCD using the division algorithm. It is called the Euclidean algorithm. That will be the next lecture in the next time. So, ladies and gentlemen, this was a pleasure seeing you guys. So you have time to look at those. Probably one of the other things I'll do is I may make some extra lectures to build on this. But please feel free to reach out in case you have comments or questions. Otherwise, it was a nice meeting you guys. And I don't know, you can give me feedback on whether this approach to life is good.